Hi there, I'm Voice Loop. What should I call you?
You can call me Ronan.
It's nice to meet you, Ronan. I'll call you Ronan from now on.
Okay, can you count up to 10, please?
One, two, three, four,
Sorry,
five.
if you don't mind, could you count down, do it backwards?
Sure thing, 10, 9, 8,
And
7.
if you don't mind, could you skip every second number, please?
I guess so. 10, 8, 6, 4, 2.
All right. I'm wondering if maybe,
I'm listening, Ronan. What are you wondering?
yeah, I was thinking maybe you could give me a recipe for pancakes.
Sure, I can help with that. How many people are you trying to make pancakes for? That'll help me suggest the right amount.
Yeah, it'll be for 4 people. Keep it very brief.
All right then, here's a quick one for 4. You'll need about 2 cups of pancake mix or flour, plus maybe a bit of milk.
In this video, I'm going to demo Trelis Voice Loop. It's an agent, a voice agent that runs on your Mac and is defined by less than 500 lines of Python code. It includes some more advanced functionalities like turn detection and allowing for interruptions, things that are only possible now with some models that have lately been released like Gemma 4 or like Pipecat's Smart Turn v3. This is designed for developers as a starting point for building voice agents. And it's aimed to be modular, so you can plug in different models, you can plug in different features, while just remaining compact and giving strong baseline functionality. I'll talk through as well some of the limitations and maybe some of the plans for where this will go. You can access it all on Github under the Trelis Research Organization. So what we have in this agent, first of all, is we have voice coming in. So voice comes in to microphone, and then this is going to be transcribed. And it's transcribed by Moonshine base by default, which is a small transcription model. Then that text is taken. So we take the text and we pass it in, just make it a bit bigger, to Gemma 4. And then Gemma 4 will give the text out. So we've text in from Moonshine, and then we have text out, and then we take the text out and we put it through a text-to-speech model, which we're using Kokoro for, and then that gives the voice. So when I speak initially, that's transcribed. It's actually very fast because Moonshine base is a very small model. And then that gives us text out, which goes through Gemma, which is also fairly fast, and then goes through the text to speech, which is also fairly fast, although if you're producing a lot of speech, that can be a bit slower. So if there's a lot of words in the response, there can be more of a delay. Now, there are a few challenges if you just pipe this together. I mean, it's not necessarily easy to get this pipeline working, but even if you have it working, the next problem you run into is turn detection. So you'll notice that when I was speaking at one point, I started to hesitate. And if I'm hesitating, I don't want the agent to respond, which means I need some kind of turn detection. I need to have a model that says whether I'm finished speaking or not. And you can see that clearly in the transcript here. I start to say, yeah, I was thinking, yeah, maybe. And I don't want to finish here with a response and get a response from the agent. I want the agent to wait. And that's what's happening here. The smart turn model is basically saying the probability of Ronan being finished is only 4%, 1%, 6%, 4%. So while the probabilities of me finished are being finished are low, it's not going to respond. And then when I do finish here with a phrase that sounds like I'm finished, the turn probability eventually goes up. And by the way, if you just wait with a silence, the chances of a new turn being needed will also go up. So for this reason, you need to incorporate here, after the voice coming in, you need to actually have a few steps. First, you have voice activation detection, which says, is this speech or noise? And then you need to have something like Smart Turn. So Smart Turn v3, which is a model from Pipecat, it's open source. This basically says, is this person finished speaking or not? So that's the first problem you need to handle, which is turn detection. And you'll see it's not exactly perfect, because in this case, I think right up here, I was saying, I'm wondering if, and it actually thought I was finished, and it gave a response, I'm listening. Whereas here, it correctly detected I was thinking, and it waited, and then gave a response. Now, humans obviously won't be perfect either at this, but you can get a sense for how turn detection is working. The next problem that you hit is you want to know whether somebody is butting in, if it's an interruption or not. And normally, if I just play the text back, the audio back rather, from my computer, which you were able to hear, when that audio comes back, if I just have a simple interruption rule that says if you hear a noise, then that's an interruption, that's going to fail, because I'm just going to hear, it's going to think that its own voice being played back through the speaker is an interruption. And the only way you solve that, or one of the ways, is to use echo cancellation. So when the voice is being played on my setup, I also need to add in an aspect here of echo cancellation. So you can kind of think of it like in 4A, when I'm playing the voice while playing TTS, the text to speech, use echo cancellation and use voice activation detection. So basically, while the speech is being played back, that echo is being cancelled, and then what's remaining, which should be my voice or my interruption, is being detected using voice activation detection. And if my voice is detected there, that counts as an interruption. So here, for example, when I interrupt, I think I interrupted back up here, it's seeing there's a voice interruption because it's cancelling the echo from this being read out. It's then using voice activation detection on my words, where I'm saying, if you don't mind, could you count down? And it considers that as an interruption and then stops playing the TTS and will start to again listen to me and then go to Gemma for doing the feedback. Now, this will work fairly well. There's one more layer of nuance that I'm not covering, which is the distinction between whether I'm really interrupting or whether I'm just agreeing and saying, oh, yeah, that's right. And that's called back channeling. Currently, there's no detection of whether I'm actually interrupting or whether I'm back channeling. There are models that will support that. I'll probably cover it in a later video and include it here in this voice loop. But broadly speaking, even if you have this kind of interruption detection like is in voice loop today, it's generally going to capture most of the interruptions. Sometimes it might accidentally interrupt when you don't want it to, but the agent should respond, and then you can kind of continue on from there. So this covers most of the features of how voice loop works. There are a few other things I want to note. You'll have heard in the audio that there's a chime. So when we're waiting for the agent's response, you can turn on a chime so the user knows that something is happening. You can also drop that out, although if the latency is longer, the chime can be helpful from a user experience standpoint. You can also turn on memory with the flag memory. What this will do is after every step, it will run the language model Gemma over the response and see if anything should be written into a memory file. It would be written in here to this file, and then it would start to say things like the user's name is Ronan. And then when you replay the conversation, it's going to come back and remember those things. Every, I think, 5 or 10 turns, it will then consolidate the memory. So if you've got multiple memories written out here, it will consolidate that. So it's a fairly simple form of memory. You can also opt to operate without any TTS. So for example, here, I could just rerun this with no TTS. And in this case here, it's not going to read anything out, and it's just going to respond with text, which is going to be fairly fast. So yeah, if you can just call me Ronan, please. Yeah, no, sorry, Ronan, R-O-N-A-N. Yeah, we'll talk. So you can see here, it's just giving text as the response. And then if we run with TTS, it's going to overlay the voice production there as well. And you can see how the smart turn detection in this case is a bit inaccurate. It took quite some time to respond. So possibly a chime could be added there for improved UX. But yeah, you can see the kind of performance of the turn detection. And depending on your application, you may need to tune the turn detection model, which is again, something I'll hope to cover in a later video. This flag allows you to turn off the audio echo cancellation. I discussed how echo cancellation allows for interruption because it wipes out any of the echo from the text being read out. So you can turn that off, in which case the interruption detection won't work at all because it'll just keep getting interrupted by itself. You can choose which voice from Kokoro by picking one of the ones below. You can also choose to use a smaller model. You can actually use, I'm using the E4B, which is a 4 billion parameter model. You can use the 2B. It works okay, but the logic is not quite as strong. You can see the logic is reasonably good. It's able to read back, count down every second number, so it can do some reasonably advanced kinds of reasoning. You can also customize the silence timeout. So if there's a certain amount of silence, then you'll get a response back. And you can also record. So you can have some recordings of your full conversations if you want to play them back. Now, there's one more advanced thing I want to talk about, which is that in principle, the Gemma model allows for audio input as well as text input. So I think there's an option where you can put in the audio mode, and I'll just try it here, see if it's working. I think it's called audio mode.
Hi there, I'm Voice Loop. What should I call you?
You can call me Ronan, please.
Okay, Ronan. I'll call you Ronan from now on.
Great. Can you give me a recipe for pancakes, please?
Sure, I can. How about a classic recipe? You'll need a cup of flour.
Okay, that's great. You know, if you wouldn't mind, can you just go to counting down from 10, please?
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Okay, that's great. Can you count up from 1?
Sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Great. So yeah, actually that worked. In my experience though, when I use the audio input for running, it can be not as reliable as first transcribing it. And I was suspecting this is partly due to model size. Definitely when I use the E2B model, it's not quite strong enough to handle the audio input directly into the LLM. But this 4B model seems to handle it somewhat better. Also, yeah, when I use the audio mode, it seems like sometimes it's not trained on conversational data, so you're not able to get it to hold the conversation. It will start to lose track. And furthermore, the library for MLX that's being used right now, it only allows you to inject the very last turn of audio. So for the conversation history, I'm still passing in the text as transcribed from Moonshine. So I'm doing two things in parallel. I'm always transcribing with Moonshine to keep the history, but I pass in for the most recent turn only the audio. Now, the benefits of this in principle are if you could pass in audio, you can potentially over time manage to, well, not over time, you'd have to actively do some training on the model so that the audio can be used to do some kind of turn detection or interruption detection. That's not something that's supported, but in principle, if you do input audio, you should be able to allow the model to just go off of that audio for deciding on turn detection and to decide on interruptions. So this is kind of the direction of travel right now. These end-to-end models are still Cascade models. They involve speech to text, then an LLM, then text to speech. But over time, the direction of travel probably is to have a more integrated flow where we have a fewer number of neural nets that are able to provide support across. Right now, that's difficult because to get good reasoning, you typically need to resort to an LLM that is strong and that has a lot of pre-training data. And if you move away from that and try an integrated model, you're just not up with having the frontier level of intelligence, which is why we end up cobbling together these models so that you have a first transcription part, then a strong reasoning model, and then a model that will go back to speech. So check out the repo online. If you have any questions, as usual, just let me know down below in the comments. Cheers, folks.